So the first talk is going to be by Ali Wakilian. He's a research assistant professor at TTI Chicago, and he will be talking about learning online algorithms with distributional advice. Over to you.
That's good. Okay. Can you hear me? Yeah. Thanks, Ravi, for the introduction. Thanks, the organizer, for organizing this workshop and inviting me here. So yeah, I'm going to talk about learning augmented algorithm, in particular, talking about online algorithm with distributional advice. Okay. Okay. So what's the whole motivation behind this this direction in this area? So we have seen lots of successful performance from machine learning in different applications, like in object recognition, in speech recognition, machine translation, and in almost all of them by now, machine learning are doing much better than the human. So they beat the human performance. And it's not just stop here. They can do some fancier stuff. Like, you can give them a sentence and they will come up with an essay or paragraph at least. Or in 2017, the machine, just a deep learning based algorithm could just beat the rank 1 Go player. So, we have seen lots of these application, and you can think of more in whatever you, based on your research direction you're considering or a specific problem that you're interested. For sure, you can see that machine learning is doing very well in that domain too. So, but what it says to us as an algorithm designer or as a person who is interested in theoretical computer science. So one way of thinking about it, if we can use these machine learning approaches or the success of or this power of machine learning in classical algorithm. And by classical algorithm, I mean just the type of algorithm you have heard so far, or even more classical algorithms. Okay, so let me tell you, in high level what we are looking for here. And this is called learning-based algorithm or algorithm with prediction. And actually, you will hear more about it, I assume, tomorrow at least. Nicole is here, so yeah. So the idea is as follows. So suppose somehow magically, or it's not necessarily magically, even if you can maybe use previous data to get such information, you are come up with a prediction, right? And that prediction provides, some useful information about the input, or it could be just a garbage and has no use. So that's the type of guarantee that we would like to provide, given the prediction that we received. So we would like to provide a better performance if it happens to be the case that the prediction is saying something useful about the input, and it's going basically to provide accurate information about the input. And this is something that should be formalized, but this is the high-level idea. But the whole catch is that we don't want to blindly rely on the prediction. So basically, we would like to make sure that even the prediction is completely off, we still get some bound, which is similar to the worst-case guarantee that we already know for that problem. So basically, in some sense, we are shooting for the best of two worlds. If machine learning is going to do well, we would like to match its performance. Otherwise, we would like to be able to at least recover the performance we could achieve by just our own algorithm, classical algorithm. Okay, and as this book has been mentioned already several times today, so it's also part of this beyond worst case analysis algorithm. So this is another way of thinking about this direction too. Okay, so let's maybe do it a bit more formal. So in particular, I receive an instance I of problem P, and then there is a prediction or advice about this input. And my goal is to design an algorithm that if the prediction is accurate, then I'm getting close to the optimal solution for this instance. But otherwise, even if the prediction is not accurate, I would like to be comparable to the best, the performance of the best classical algorithm. when it runs on P. Okay, so I mean, it's in particular very popular for online problems. So, and this is some natural motivation for that, because in online setting, you don't see the entire input at once, right? So this is a natural place to get some information about the future data, right? So, and that's why people have specifically looked at this setting in algorithms with prediction. And beyond that, I mean, besides the online setting, people have also studied in learning theory, data structure, streaming and sketching, and combinatorial optimization in general. Okay, so what I'm going to talk about today is mostly about the type of advice that we get about the problem. So initially, the most papers on this algorithm with prediction consider deterministic advice or deterministic prediction. And here we are aiming to provide looking at some sort of distributional advice or prediction and see what we can do there. So for instance, as a very simple example, which is also considered mostly in this setting, I mean, with deterministic advice. So let's consider a ski rental problem. So in this problem, just to make sure that we are all on the same page, so there's a person that wants to go to a ski, and in each ski day, I mean, it's each day basically the player decide whether he should want to rent the ski shoes or want to just buy one, right? And the whole issue is that he or she doesn't know for how long he or she is going to go skiing, right? So basically, the optimal strategy depends on the fact that if it's going to go for skiing for a long time or just for several days. And here we assume that the cost for renting the skis is 1 and for buying the skis B. So basically, if you are going to go more than B days, then it's better to buy, but otherwise it's better for you to rent. But this is the information that we don't have. So basically, the goal is to minimize the cost paid by the player. And in the classical online setting, we know that there exists an algorithm with competitive ratio E over E minus 1, and this is basically the best we can do. Okay. And as I mentioned, I mean, this problem has been studied with deterministic advice, and in particular in the work by Ravi Kumar, Manish Rohit, and forgot Zoya, I guess, yeah. But there they consider deterministic advice, which means that they receive a value y, which says that okay, you are going to go skiing for y days. But you cannot just completely rely on that value because it's not, there's no guarantee that it's the correct value. So they show that how we can use this extra information so that we can get the best of both worlds guarantee that I described in the earlier slide. But as I mentioned, I mean, the whole motivation here is that in practice, usually it's harder to come up with a deterministic advice. And what we usually can provide is some sort of distributional advice. So it's easier to say, okay, with a good probability, you are going to go skiing between 10 days to 20 days. I cannot give you the exact value, but it's likely that that would be the value that you are going to go. Okay, so or other distribution, for example, it's more like exponential or more like a normal or something else. So, but it's more natural to come with the distributional type advice because it provides both confidence and more options. Okay. So, and just as I'm going to switch to the distributional case, I need to just set up the type of optimization problem that I'm considering. So here we have, I'm looking at the minimization problem P. Like, for example, a ski rental, we want to minimize the cost. And I assume that there exists an unknown distribution on inputs of P, unknown distribution D of inputs P, and basically means that the instance is drawn from a distribution D. And then we would like to find an algorithm that minimizes the expected cost. Okay, so I would like to come with a strategy that if I compute the expected cost, then according to distribution D, it's minimized. Okay. So now what's the type of distributional advice that I'm considering? So here we assume that the input or the advice that we receive is that, okay, consider this family of distribution. Your input is drawn from one of this distribution in in the family of distribution C. And now we would like to design an algorithm that alpha consistent and beta robust. So basically, these are two parameters that are important in this learning-based type algorithm. So by alpha consistency, it means that if the actual distribution is from the family C, then we would like that the expected cost of our algorithm is less than alpha times the optimal strategy for that distribution D. Okay, but otherwise, we would like that our algorithm return a solution on D that is comparable with the optimum online strategy that do not consider anything about D. Okay, yeah, as if just ignoring D. Okay, and just maybe a bit of more motivation. So, I'm providing some family of distribution of the input. So, for instance, it's clear that for the population, I mean, for the resident of Zermatt in Switzerland, I mean, the distribution of going to ski is much more different from a person like me in Chicago, right? So it's a completely different access to these resources. So we could have a different distribution here rather than there. Okay. Actually, I wanted to mention Chennai, but I realized that there is a snow kingdom here. So it's one of the main attractions apparently. So I just get back to Chicago. Okay. So yeah. So that's maybe the motivation. So maybe you can provide with a family of distribution for different population or demographic or inputs that you consider, but still you are not sure. Okay, so I want just to mention that maybe, I mean, there are many experts in online algorithm. I'm not, to be honest, that expert. So, so it's very relevant or very related to the diffuse adversary model. And for instance, I mean, this was by Koutsoupias and Papadimitriou, and they define it for the paging problem. And there, what they do is that they again consider minimization problem. They have an unknown family of distribution C on the input. Yeah, on the collection. But their goal is to come with the algorithm that minimize the expected cost of algorithm over this distribution over the optimum algorithm for that distribution. Okay, but here there is only that distribution. Oh, okay, actually I forgot to mention something. So here, one thing that's important in our model is that, so we assume that we have this collection of distributions, and we further get IID sample from this distribution. So basically, our work is more like a learning theory with the online algorithm. Okay. So here, the main difference, the first difference is what I forgot. The second difference basically is what I forgot to mention earlier. So here they do not have any sample access to the input, just they have distribution and they want to optimize it. And the other one is that they look at the instance-wise optimal, but we look at the optimal for the distribution when we are looking at the optimal policy. Okay. So, I mean, the first observation is that we basically, I mean, if you consider the sample access to this problem, it's not just suffices to have the sample access. Basically, this predicted distribution or family of distribution is somehow necessary to get something meaningful. And by meaningful, I mean to be able to beat the E over E minus 1 competitive ratio that we know for online algorithm of skew rental. So basically, if we do not have any information about the distribution and want to sample from the distribution, then we need infinitely many samples to be able to do something interesting. And that's relatively easy to see. I mean, you just need to have basically a distribution supported on 2 points, like a 0 and I times b for different value of I. And just you can see that looking at this family of distribution, you cannot, and why I choose this this distribution, because as long as I is less than b, then it's better to buy. But once I becomes greater than b, then you have to, sorry, the other way. When I is less than b, you have to rent, but otherwise you have to just purchase. But it's hard to distinguish between these two cases if we do not have enough samples. And the enough samples basically should be larger than S. But as you can consider large value of S or any arbitrary value of S, basically you cannot come with any strategy with finitely many sample that can do better than E over E minus 1. Okay, so basically, yeah, we need this distributional assumption on top of the sample access to the inputs. Okay, and so this is basically the result I'm presenting in the rest of the talk. So we show that there exists an algorithm that draws 1 over epsilon square many samples and output lambda times 1 plus epsilon consistent and lambda over lambda plus 1 robust strategy for a skew rental on log concave distribution. Okay, and we show that basically this sample complexity is optimal. So basically, we need at least omega 1 over epsilon square sample to get a 1 plus epsilon consistent strategy. So just, I mean, if you're not familiar, log concave is a very rich family of distribution. And formally is the type of distribution whose density function is of form e to the f of x, where f is a concave function. For instance, exponential is a type of log concave. Okay, and just want to make clear that what we are doing, we do some sample complexity analysis, and we show that we can use the robustness guarantee that's achieved by the result of Mahdian, Nazirzadeh, and Saberi, where they show it for resource allocation problem. Actually, this is a result that's very important in this area, but somehow got neglected in at least earlier in the development of the areas. So it's good to maybe to recap it. Okay, so this is the plan for the rest of the talk. So the algorithm has 2 main components. So in the first part, we show how we can get an epsilon additive strategy. So basically, we show a strategy with cost at most opt of d plus epsilon. Okay, and this is assuming that that the distribution is coming from the collection that we have received as a prediction or advice. And then we analyze the cost of the optimal strategy for low concave distribution. So basically, in short, we show that the optimal strategy is always to buy initially or rent indefinitely. Okay, so for this family of distribution. And basically, that is what we really need for our analysis, nothing else from low concave. For example, if you're familiar, something like monotone hazard rate distribution also satisfy this condition. And I mean, we can show that for those distribution also this holds, and it's a bit more general distribution too. But I mean, for sake of this talk, let's consider just log concave. And then we show that we can, by these 2 components, we can show that we can basically get a multiplicative approximation from this additive guarantee. So basically, when the optimal strategy is either buy initially or rent indefinitely, then we pick some samples from distribution, and based on the CDF of the sample distribution or empirical distribution, if this holds, I mean, basically it means that if the probability that the person over the sample instances is going to skew more than b over 2 is large enough, then the optimal cost is at least b over 6, and it's easy to see that the additive is basically a multiplicative. And in the other case, if it doesn't hold, then we can show that the optimal strategy is basically simpler. It's just rent forever, because in that case, the cost of this strategy, which is just the mean of distribution, is basically the best. And here is the part that we rely on the fact that the optimal is whether buy initially or rent indefinitely. Okay, so that part is also simple. So in a sense, we can just do a simple test over the sampled instances and see whether we should, and then we can basically come up with a 1 plus epsilon approximation. Okay, so now let's go to the design of additive strategies. Okay, so here is the result that we want to achieve. So for any epsilon greater than 0, we want to show that 1 over epsilon squared samples from D suffice to design an epsilon additive strategy for a scalar problem. And this additive guarantee holds for any distribution. It doesn't need to be log concave or any specific one. Okay, so just to recall, I mean, I'm not going to cover the whole analysis, but maybe just to give you some intuition how the proof goes. I mean, I provide some statement that could be helpful. So first of all, I mean, it's easy for a ski rental problem. It's easy to see that the optimal strategy is just a threshold strategy. You just wait till someday and then buy, right? Because once you buy it, I mean, there is no benefit. You can always use it. I mean, you don't need to rent, and that's easy that the whole meaningful strategy are like this. So this is the deterministic strategy, and for the randomized one is also just a distribution over these threshold strategies. Okay, sorry for, again, the same problem with the PowerPoint, but yeah, forgive me. Okay, so now that we know that the algorithm is basically a distribution over threshold strategies, we can just rewrite the cost function as this. So basically, Q is the distribution of the time of buying. Okay, so basically, I mean, yeah, you can see that basically the cost would be as follows. So basically, we just get the T from distribution Q, and then assuming by sampling X from the D, then it's just when X is less than T, we are renting, so the cost would be X, and otherwise, if X is larger than our threshold, it means that we have rented for the first T days and then buy it. So the cost would be B plus T. And you can also find the optimum cost by the similar equation. Okay, and this is our algorithm. Quite simple, right? So we basically do the following. So we sample endpoints from D, and is something to be determined. And then we compute the empirical distribution, and then we find the optimal, stopping threshold for the empirical distribution. And it's also easy. If once you have a distribution, the optimal strategy or the strategy is always deterministic, right? So you don't need to do randomized. And then we return the minimum value of T prime and this value, E log B over epsilon. Okay. So just to give you a sense how we can, what was the sample complexity? The only thing that we need in our proof is we need that the sample distribution, it has a small Kolmogorov distance to the original distribution D. And then, I mean, we can just use the DKW result, and it's easy to see that the number of samples that we need is as follows. Okay, but the whole thing that matters for us, I mean, we know that relation is basically tight, so is the fact that Dn is with a small Kolmogorov distance from D. Okay, and this is the observation that we have. So if for two distribution, their Kolmogorov distance is small, and if there exists a stopping strategy with T prime and T star, such that the optimum, basically using T prime on D prime is the additive, basically is epsilon additive approximate solution, and using T star on D is epsilon additive strategy, then basically using T prime on D is also, in some sense, epsilon time that term additive strategy. Okay, and here we use the fact that we need that the stopping threshold has to be small. I mean, the smaller they are, the better for us, because then we lose less in the additive term. Okay, and this is why I have this term, and actually this is needed for that purpose. And we can show actually there exists always a good solution with that property. Okay, and so once we have this, so basically this is one of the claims. So there always exists such a stopping time, T, less than, I mean, like B over log B over epsilon, that achieve an additive, epsilon additive approximation. Okay, then just by combining the result from this slide, we get, we can come up with this statement that an epsilon additive strategy for the empirical distribution is an order of epsilon additive for the original distribution. I'm not going to talk about the details here, but that's basically what matter for our analysis. Okay, so this was the algorithm, was pretty simple in some sense. So we compute the empirical distribution, find the optimal solution over that, and pick these two, minimum of these two values. Okay, so what we have seen so far is the following. So we know how we can get a consistent algorithm. So we know an algorithm that if the input is truly drawn from the predicted distribution, then we get an alpha approximation, which could be better than the E over E minus 1. That was actually 1 minus epsilon. Now, we want to also guarantee the robustness. And here is the part that we rely on basically this framework of Mahdi Anatol that I mentioned earlier. And this framework actually works for the more general problem of online resource allocation. So let me just very briefly tell you what is this and what the algorithm is, but I'm not going to talk about the analysis. What's a very simple one. So basically in online resource allocation, we are given a sequence of jobs, J, and we also have a sequence of servers, S. And at each time, a new task, I mean, a task J of T will show up, and we need to assign it to a set of servers. And for each, and this is the part that we can choose from the servers. So each server Si has an activation cost Ci and a serving cost Di. Okay, for instance, you can think of facility location or many other natural problems. And for instance, the SQ rental that you will show next is a very simple special case of this problem. And then the goal is to find an assignment with the minimum total cost. So we should compute both the activation cost for the server that we have activated and also the serving cost for the servers who have served any jobs. For instance, in the case of SQ rental, we have two types of servers. One is the buy server, and the other one is the rent server. So in the buy server, you have the activation cost of B. So once you activate it, I mean, then you can use it forever. The service, basically the serving cost is 0. And there is a rent, basically, server, which is has activation cost 0, and then the serving cost is just equal to 1. So basically, you are renting. Each time you rent, you have to pay the serving cost. Okay, and then that's basically the algorithm, how it works. So basically, they consider if we have two strategy for this problem, let's say resource allocation, and here we consider the SKU rental, then we can basically trade off between the guarantee of these two algorithms. So basically, we at each step we check if the cost for algorithm A is less than 1 minus the threshold that we have times the cost with the strategy B, and if it was that, we follow the advice of A, and otherwise we follow the advice of B. Okay, so this is a very simple framework that can be used for many problems and gives us readily this consistency robustness trade-off, gamma and gamma over gamma minus 1. Okay, and that's what basically we are going to use here. And oops, sorry, yeah, we don't have it written as a last session, but that's exactly the consistency robustness guarantee that we get. And that's actually what, for instance, in the original paper of Ravi Kumar et al. For SKU rental with deterministic prediction, they get the same consistency robustness. Okay, and I mentioned also this is the sample complexity that we achieved was optimal. So I'm going to say a few words about that. But just before that, how much time do I have? Or 10, 15? Okay, yeah, it will be more less than that. Okay, so yeah, I want to show that 1 plus epsilon multiplicative approximation on log concave requires omega 1 over epsilon square sum. And for that, we just consider two exponential distribution D1 and D2 with the following rates. And the useful properties here is that the optimal strategy for D1 is to buy in the beginning. And the optimal strategy for the other distribution is just to rent forever. And they have, I mean, the gap between them is large enough. And then we show that to solve the SKU rental on this problem, it's equivalent to distinguishing between two exponential distributions whose mean differs by order of epsilon. And this is a classical result. Lecomte-Lemaître will tell us that to basically distinguish these two exponential distribution, we need to have at least omega 1 over epsilon squared many samples. Okay, so this was basically one of the results that we have in our paper. And what I want just to give you some idea, I mean, of this distributional type of advice. And hope that, some of you become interested and maybe work on it. I mean, I believe that is maybe not the best way of defining it, but it's hopefully will lead to some further work on it. Okay, so for instance, we consider other direction or for instance here, other sample access to distribution. So one sample access which is common in distribution testing is conditional sampling. So basically you say, I want to see if there exists any, or pick an IID random from distribution with value at least X, right? So basically you're getting rid of the tail of distribution. So if we have such access, then we can get basically, we can show that for any distribution, we can achieve 1 over epsilon to the 4 conditional sample to get 1 plus epsilon multiplicative approximation. And the other problem that we consider was the profit inequality. So you will see talk about profit inequality tomorrow. But yeah, that's with the same approach, I mean, we can show that consistent and robust algorithm. And just want to, as I mentioned, I mean, the whole point of this talk was trying to convey that considering maybe distributional prediction about the input. And there are other results that consider this basically line of research. So for instance, one is by the Mala here. But what they're considering is that they assume that there exists given a prediction X, and the actual number of days that you go skiing is basically, there is a basically joint distribution between this prediction X and the actual number of days that you go skiing. And now their goal is to come up with a stopping time function X that is learned from this distribution. I mean, you can, of course, ask them about more details if you are interested. And with that, let me just conclude the talk here, and let me know if you have any questions. Yeah.
Randomize that following sense. By Gauss principle, we know. So even
Nope. Yeah, that's true. Yeah. That's actually a very good point. And I guess, but that distribution is not log concave. No, it's only if the distribution is found log concave, then you get that. Yeah. But otherwise, you get just the E over E minus 1. Yeah, that's a good point. And actually, for the same reason, I mean, we cannot do it for general distribution. Yeah. Yeah. Right. Yeah, but still, you can say for some maybe a special distribution, and that they could be still helpful, and that's, for instance, what we consider here. But yeah, your point is completely right. Thank you.